Hello class, these are our notes for Calc AB 3.9 differentials. So first we're talking about a tangent line approximation. So what we're getting at for tangent line approximation is we're using a tangent line to approximate a graph. So we're using a tangent line to approximate a graph. And it's really only accurate for points close to the point we have the tangent at. The farther we get away from that point, the less accurate that tangent line is going to be. So we have a little picture of that down here. So you'll notice we have some kind of a sine curve here, and I have a point here on my sine curve, and then we've got our tangent line to that point. So when you are really close to that point, the tangent line and the curve are almost the same. So they're almost on top of each other here and here and here. And then you can notice that they start to get further away from each other the farther we get from this point. So the farther we get from that initial point, the farther the tangent line and the actual graph veer off from each other. So we're talking about using that tangent line because it's maybe easier to use to approximate our graph really close around this point, around that point that we've drawn the tangent line at. So that's kind of the goal of what we're doing today. So for this top section here under tangent line, what your book wants us to add in, which is kind of what we have down here under differentials, but don't worry about that yet, is they're talking about using the point slope form of a line. So if you think of point slope is y minus y1. I'm going to write that at the top. So your point slope is your, I cannot get this to work this morning, y minus y1 equals m times x minus x1. Only if we're using a tangent line, our slope is really our derivative at some point, and then that point is what we're using for our x1, y1. So our x1, y1 would be c comma f of c. So if we fill all those things in, our tangent line approximation would be y minus f of c equals f prime of c times x minus c. And then if we take it a step further and we solve for y, we get y equals f prime of c times x minus c plus f of c. Okay, so we're going to first do a little tangent line approximation for this function at this point. So we know first thing we always have to do is find our slope. Our slope is going to be our derivative, and we want to find that at the point. So first step is taking the derivative. So let's go ahead and find f prime of c. So we have to take our derivative of this function. Derivative of 1 is 0. Derivative of sine x is going to be cosine x. And then if we want to find our slope, we want to find our derivative at that point at 0, 1. We want to find the value of the derivative at that point. So that means my x is 0, my y is 1. We only have an x here. So my slope at 0, comma 1 is going to be f prime of 0, which is going to equal cosine of 0. So if I think about 0 radians or 0 degrees, that would be a point right here. My x is 1, my y is 0, so my cosine is really x over r, so my cosine is just going to be 1 here. So I end up with a slope of 1. So now I've got a slope of 1, I've got my point 0, 1. That's really my c comma f of c, right? So to write my equation of my line, I would say y minus my y1 is 1, and then slope times x minus 0. And I could definitely rewrite this. I could write y equals 1 times x minus 0 plus 1. But it feels really weird to have that x minus 0 in there. We'd probably just want to write x plus 1. Okay, so this is the kind of problem we've been doing all along. It's just now they're calling it something different, right? They're saying tangent line approximation. So I could use this to approximate points really close to 0, 1, couldn't I? I could say I want to know what's going on when, let's say, x equals 0.2, right? That's really close to 0. but it would give me a y value. So I could say like 1 plus sine x is just too complicated. I don't want to use that function, but I want to have a good idea of my y value at 0.2 because 0.2 is really, really close to 0. And then I could plug that in and I could get a value. So that's what a tangent line approximation does. So I could use this function right here to figure out my y values instead of actually using y equals 1 plus sine x. And they give a little, oh, this is really cool. So in the table, they kind of show you that as well. So they're showing you that at that point at 0, 1, my y and my actual function. So my y using my derivative, right? So this is like my approximation. Okay, so maybe we should write over here. This is my actual value, and this is my approximation value. And my actual and my approximation are the same. As we go further away from those points, it gets a little bit less accurate. But if you look at like what happens when our x is 0.01, well, our actual function value is 1.009998, and our approximate is 1.01. So they're really, really close. But as we get further away from 1, they get a little bit less accurate, but still pretty darn good, right? And using our approximation is a lot easier than plugging something into f of x is 1 plus sine x. So that's what this is all about today. Okay, so let's go ahead, now that we've got this idea of what tangent line approximation means, we're going to talk about differentials. So let's launch into our best explanation of differentials. So first of all, we've got this idea that we've got a tangent line approximation, right? So here's my point, c comma f of c, and here's my tangent line approximation. Okay, so now we're looking at, well, what happens when we have that point that's a tiny bit away, right? So just like we looked at points up here in our table that were a tiny little bit away from x, we're going to look at that on the graph also. So this little bit that we are away from our x from 0 to 0.01, that is going to be our delta x. And then we have an approximation. So we have like the amount that we are kind of off by for y, and then we have the amount that we're actually off by for y. And those are going to come into play here in just a second. So let me kind of scroll this up so we can see everything at one time. And if I'm looking at this point right here, this is on my actual graph. So this is on my actual graph. And I'm looking at this point right here, which is on my approximation graph. Okay. And I'm writing right in the middle of all the stuff I need. So I probably don't want to do that. So let's say this is our approximation graph. And so for both of these, we're looking at a point that is delta x away from our original. Okay, so here is my original point c comma f of c, and I've added a delta x to my c. And so delta x is like a small amount of x. This point here is also a small amount of x away from c. So then we have the difference in y values, right? So like my y value should be right here on my graph, but instead it's down here. So what's going on is my change in y value. So from my original y to my new y, my actual difference on my actual graph is delta y. My difference here from my, where do I want to put this at? So looking at the difference between my approximation and where I should be at is going to be our delta y. But when we look at how close we are, we're going to use this value instead. So I feel like I'm not doing a very good job of explaining this. So maybe let's go through the math over here. So this is what we had up above. We all agreed this was how we wrote the tangent line. And this is used to approximate the graph of f. The quantity x minus c is called the change in x. So x minus c is that difference that we have from our original graph. and we're using a delta x for that. And I think I did a pretty good job of showing you delta x is a distance away there. So when our delta x is small, the change in y, which is denoted by delta y, and this is our actual change, can be approximated this way. So, and we can call this pretty darn close to our derivative times our delta x. Probably not any better. I think it's really hard sometimes, these things. I feel like I understand it really well until I have to explain it out loud. And then I'm like, wow, this is kind of a disaster. So let's go through a math problem. And I think the best way to do this is kind of to look at our actual and our approximation. So we're going to be looking at our actual and our approximation. So our actual is going to be using the delta stuff, the delta y and the delta x, and our approximation is going to be using differentials. And the differentials are our dx and our dy. So if I wanted to find what's really going on here, I have this graph, y equals x squared, and I have a value of x equals 1. But then I want to know at what's going on a little bit beyond that at 0.01. So this is the part that I'm actually doing first. Okay, so if I'm looking at my actual and I want to see what my change in y is, right? That's what delta y is. So first I would look at what's happening when my y equals 1. So if I have at x equals 1, I have y equals x squared, which is y equals 1 squared, which is y equals 1. So now I want to know at what happens a little bit beyond that when my delta x is 0.01. So that means I want to know what's going on at x equals 1.01. Okay, so my change in my x's is equal to 0.01. That's my change from one x value to the next. So it's really close to 1, but it's not quite at 1. So in that case, I know that y equals x squared, which is y equals 1.01 squared. And fortunately, I calculated that out earlier, and it is 1.0201. So if I want to find my delta y, I'm looking for this difference. I'm looking for the difference in my y values. And so 1.0201 minus 1 would just be 0.0201. So the other way we could get that, the other way we could get our exact delta y is by taking f of x plus delta x. That's what we did right here. This is our f of x plus delta x, x plus that tiny bit more, and we subtracted just f of x. This was our f of x right here. So I really think, though, to calculate them separately and subtract makes more sense than to like set up this formula and do it that way. So our actual change in y, so what happens is we increased our x by 0.01, and then our actual change in y was 0.0201. So what differentials are telling us is that we can approximate our delta x and our delta y. We can approximate those instead using dx and dy, which is a derivative. So to do our approximate of the using the differentials, what I'm going to do is I'm going to take y equals x squared, and I'm first going to take a derivative. So derivative of y would be dy dx. Derivative of x squared is 2x. And then we're going to essentially think about how if we multiplied both sides by dx, we would have dy equals 2x dx. Okay, and then I'm going to say that my dx is really basically like a delta x. So whatever I used for delta x, I'm going to also use for dx. So now we're doing this thing right here. Again, I think it makes more sense to do the actual first and then the approximation one. So let's go ahead and plug in some values here. So what's cool about this one is I don't have to work it out twice. I don't have to subtract them. I don't have to do any of that. All I have to do is take a derivative and say, well, dy is a pretty good approximation. My derivative, based on this graph right here, is a pretty good approximation for the actual graph and what's going on. So now I'm going to go ahead and let x equal 1 and dx be the same thing as that delta x, that tiny little bit that I want to increase x by. So I'm going to say that my dy is equal to 2 times my actual x value that was 1 and my amount I was increasing x by, which is 0.01. And then I'm going to go ahead and multiply those together, and I would get 0.02. So when I work this out and I figure out my exact difference in my y values, it's 0.0201. When I figure out my difference in my y values using calculus, using a differential, I get 0.02. So my differential for y is literally just dy. So in order to find dy, all I really have here, dy is going to be my derivative and then my dx afterwards. So, and that's what I did here, right? I had dy dx, I took a derivative, and then I shifted the dx over. So this part right here is like my f prime of x, and this part's my dx. So this is what a differential is. And more on that in a minute. So remember, the approximation one, this is like using a tangent line, what we would get, kind of a thing. And then actual is like on the actual graph. So they're really, really close. So if we look at values that are close to our point, so in this case, our point was x equals 1. I don't know what the y value was, but the x value is the x value is x equals 1. So if we look at values really, really close to that, using our derivative to find our change in y is almost as accurate as just working out the problem twice and finding the actual difference in y. But the derivative is a lot easier. So this has a lot of implications for the real world. And that brings us to our ball bearing problem, which my husband is a former mechanic, heavy equipment mechanic for the Air Force, and I asked him about this stuff, and there's actually like a lot of real life implications of this, which is pretty cool. So I kind of want to go through this very differently than I did the original time I worked this problem out, because I like this idea of doing the actual and then the approximation using calculus just to show you how accurate they are. So we've got here that our radius of a ball bearing is 0.7 inches. So I'm going to write r equals 0.7. So that's our actual radius, okay? And then we want the measurement to be correct to within 0.01 inches. So that means we could be 0.01 higher, or we could be 0.01 lower, right? That's what that means. So that means that my delta R is equal to plus or minus 0.01. Okay, because I'm looking at actual right now. So that means my radius could be as low as 0.69. It could be as high as 0.71. All of those would be acceptable values, right? So if I wanted to find what was actually going on here, that's what I would use. I would say 0.69 is going to be less than my R, is going to be less than to within. I don't know if that means equal or not. It sounds like it means equal to me. So it sounds like our radius has to be between those two values, right? And that is actual real information here. And then we're trying to estimate the volume. And I think the reason that's interesting is if you think about our volume formula, volume for a sphere is 4/3 pi r cubed. So think about how it's not just going to be off by 0.01, right? Our volume is going to be off by more than that because we're essentially taking that radius and we're cubing it. So it's going to have a bigger impact than what you might think. So if I think about what's going on, my V of 0.69, this is where I wish I had a calculator handy, but I do not. That would be when I take 4/3 times pi times 0.69 cubed. And then if my actual one that I want would be V of 0.7. And so this is what we actually want. This is like the accurate one. And this is when our delta R is negative 0.01. And then we think about, well, what happens if it's a little bit more? and that would be the 4/3 pi times 0.71 cubed, and this is when our delta R is a 0.01, right? So those would be like all those different numbers, and we'd have to go through and we'd have to calculate them all out separately, which is great because I only have a phone calculator right now. So taking that last one and squaring it was pretty easy. This is a little bit difficult. So let's see what I can get on my calculator here. So 4/3 times pi. I feel like once I get one of them in, I can just change it and get a few different values really quickly by just changing the numbers. Okay, so if I am doing this right on my phone calculator, which you know how that is, and I want to write this equation at the top here so I can erase this and get this out of the way. So if I'm doing this correctly with my phone calculator, when I plug in the 6/9, let's see, I get 1.37. Let's go back to this fine point here. I get 1.3760552.814. When I plug in the 0.7, actually let's do 7.1 next, because I think doing the two decimal places at the same time will be easier. When I plug this one in, I get 1.499214091. And just for kicks, it's interesting to note that my husband says that having it be off by as much as a hundredth of an inch is actually a lot. He said that's probably an unacceptable amount of error, which I thought was interesting. 550402. Okay, so this middle one is what we want, but it could be as small as that, it could be as big as this, right? So I know that the 1.376 is going to be less than or equal to our actual volume that we want, which would be less than or equal to the 1.499. So our volume could vary by as much as that, okay? So I would want to actually subtract, right? Because I want to know my delta V. That's what I'm really after. So I would have to take this one right here, and I would have to subtract the 1.3760552.814. So when I subtract the smaller one, I get this. 0.60699. These are ridiculously big long numbers. Okay, so that's going to be less than or equal to my delta V, which is going to be less than or equal to, and then if I subtract the big one, what would happen? Or subtract it from the big one. All right, then that's what I get here. 0. So it could be off by as much as 0.062 or 1. So that's my actual delta V because I used my actual numbers. I said what would happen to my velocity if it was a little bit, sorry, not velocity, I just see the V, I think velocity. What would happen to my volume if I was a little bit smaller, if I was a little bit bigger? Let's work out all of these volumes. Let's figure out that difference from my actual volume. So that's my delta V. So calculus says, hey, if we're looking at something that's super close to the actual radius we want, and 0.01 is super, super close, instead, let's let r equal 0.7. Let's let dr equal 0.01 plus or minus, and let's use calculus. Let's take derivatives. So again, this was our actual over here. And most of the time on your homework, you're not working out actual, you're only doing your approximation. I just think it's really cool to kind of look at both. And maybe that's because I'm a math nerd. So we did our actual over here, now we're doing our approximation. So to do our approximation, what we do is we just say, hey, dr and dv are really close to delta r and delta v. So instead of doing all of this mess and all these decimals over here, because math people don't like decimals, let's go ahead and take our volume formula and just take a derivative. And we're going to isolate dv. So when I take a derivative of v with respect to r, I have dv dr. And then when I multiply my 3 in front, 3 times 4/3 is kind of awesome. I get 4 pi r squared. And then my last step is to essentially think about like multiplying. And I always say that in quotes, because if you think of it as multiplying, you will never do it wrong, but it's not exactly multiplying. And that shifts the dr to the other side. Okay, so now we're going to say, hey, dv is pretty close to delta v. So we're going to say dv is approximately equal to delta v. Especially at values that are really close to this. And we're looking delta V, I don't know why I wrote a D, maybe because they rhyme. And this is especially when we're at values that are really close to the R value that we want. And we're looking at R values that are 0.01 away. Okay, so in order to find my dV, I'm just going to take 4 times pi times my radius, which is 0.7, and I'm going to square it. And then I have plus or minus 0.01 here. This is a really straightforward one calculation, right? I didn't have to find the smaller one and the bigger one and then do a bunch of subtraction. I don't have to do any of that now. The math is a lot easier. This one I know I can quickly plug into my calculator. And we're going to end up with plus or minus. I don't have to do a positive and a negative, which is a big plus. And then we have 0.06158. There's a bunch more, but that's enough. We really should probably note here that when I'm looking at my volume and how much I'm off by, our units here are going to be like inches cubed, right? That's what's going on. And we should probably have inches cubed for all of them, but that's close enough. So this is going to be inches cubed. So how accurate are we? Well, it looks like our dV and our delta V, they both have 0.06, right? So they're both accurate to that decimal place. This has a 1 next and then a 5, which kind of falls right in line between those other two values. So we can see that our delta V is a really good approximation. It was a lot easier to find. So this is going to be my dV, like how much I can be off by. But then the next step of this is propagated error. So in order to find our propagated error, we have to do a little bit more work, and I don't even know where to put this. I've written so much already. I'm going to have to erase this actual part, which is kind of sad, to do our propagated error. But again, we didn't have to find the actual. I just think it's kind of cool to see, especially when you're learning a new skill, like how those are all connected. And I just really like math. So let's go through and I want to show you propagated error. It took me a lot of erasing here. So when we talk about propagated error, okay, so let me go ahead and write that over here. So propagated error. What we're talking about is basically like a percent that we can be off by. It's a percent error. You might also call it like a relative error. And basically what that is it's going to be dV divided by V and then turned into a percent. So if I knew my dV, which I already have here, and I hadn't erased my V, I could just use numbers to figure these out. But we can also do it a different way. We can also do it by looking at our dV, and our dV was 4 pi r squared dr, and our velocity is 4/3 pi r cubed. And we could just simplify this down and plug numbers in. So 4 divided by 4/3 is really 4 times 3/4, which is just 3. Our pi symbols divide out to make a 1. And then for r, I have an r left in the denominator. I have a dr left in the numerator. So it's actually a really simple calculation when you look at it this way. This is going to be, I feel like I should keep working downward, but I ran out of space. This would be, let's see, 3dr would be 3 times the plus or minus 0.01 divided by the r itself, which is 0.7. So our propagated error, if we multiply this out, is, let's see, grabbing a calculator, 3 times 0.01. I have to really watch myself to not screw anything up with those decimals. Divided 0.7, so I have 0.0428571429. Okay, so if we were going to do AP, that would be 3 decimal places. I almost feel like, I think it was sig figs in chemistry, which were always terrible, but you would look at like where the numbers actually start. I have a 428. And so if I use that, or if I think about changing this into a percent, it's going to be 4 point something percent. So 4.286%. Because if I'm going to write this as a percent, I probably need the 3 after the decimal, right? I'm just thinking about AP. And that would be our percent error. So we could be off by as much as 4%. And I think that's why my husband said, working this out, that ball bearing, the measurement off to 0.0101 inches was really, really inaccurate. I think it's because 4% error seems like kind of a lot here. You'd probably need a much smaller margin of error. We could have also gotten this by just taking that dV number and then dividing by our actual volume, which we did not do. We did it this other way, which is kind of slick. I think I would almost rather recalculate this than have to plug in all those decimals. So for example 4, we're looking to find differentials. So remember, our differential is defined as being a dy. So that's what they're looking for here, which is equal to the derivative of the function, and then basically like times a dx. So all we're doing is we're taking a derivative and then we're essentially like, again in quotes, multiplying both sides by dx to shift it over to the right hand side. So if I'm finding my derivative of y, that's going to be dy dx. Derivative of x squared is 2x. So this is my f prime of x part, and then again I want to essentially multiply the dx on both sides to shift it over and make dy equal 2x dx. So that's my differential for y. On the next one, when I take a derivative, I need to, let's see, derivative of sine is going to be cosine, and my constant just stays in front. And then we're going to shift our dx over, x and then dx. So this is what we're doing for differentials. We're just getting dy by itself. The next one, you want to think about this as being x to the negative first power. This is one that you'll probably have memorized, which is awesome. So if you have it memorized, you could just write down your answer. So we bring our exponent as a multiplier there in front, -1, x to the, subtract 1 from the exponent, -2 power. So that means dy is going to be -1 divided by x squared dx. And then our last row, so for this one, I have 2 functions being multiplied, so I've got to think of product rule. So dy dx equals, so we've got our first function times our derivative of the second, which is negative sine x, plus our second function, cosine x, times our derivative of the first, which is just a 1. So that would mean, and I want to shift the dx over. So I probably want to do one more step before I do that. This would be negative x sine x plus cosine x. I might even change the order just because of that negative sign. And so dy equals cosine x minus x sine x, all times dx. And it's not really times. It works every single time though. So it's okay to think of it that way. Last one, dy dx. Oh, I probably want to first make sure I'm thinking about this as x to the 1/2 power. So we have 1/2 x to the negative 1/2 power. So dy is 1/2 times our square root of x. You could leave it a 1/2 power, I don't care. Be really careful that your dx looks like it's kind of level with the fraction bar, or it could be on top, right? But it can't be in the denominator. That would not be correct. So be really careful about that. So having the dx here level with the fraction bar or on top is not the same thing as having 1 over 2 root x dx. Like that's not accurate. So be really careful about your placement on that. For the last one, we have a composite function. That just is kind of cluing you in that you're going to need the chain rule. And I can see chain rule because I have this outer function as my sine, my inside function is my 3x. So when we find dy dx, first we take our derivative of the outside, which is going to be cosine 3x, and then we do times our derivative of the inside. So then we're only looking at the 3x, and the derivative of 3x is just a 3. So dy is going to be 3 cosine 3x dx. So I really hope this video helps you out. I think the main ideas for today are this idea of a tangent line approximation, right? Where we can use a tangent line to approximate points that are really close to our original. And sometimes it's easier to work with that tangent line equation. It's just a y equals mx plus b instead of our actual function. And then the next part that we would want to think about is how we have calculus, and we can use calculus in this new way where we can say, hey, when we're trying to find an actual difference of something, we can just approximate using calculus instead because our values are really, really close. So as always, if you have questions, please make sure to ask. I'm happy to help you.